So welcome back, and we're on page 44, and we're going to try this question. If you haven't tried it yourself yet, please have a go at it before watching how to do it. So the first question just says, why is this little triangle on the left here similar to the big triangle? And so it's just saying, why is it, all right? And we might remember that if we've got a right-angled triangle with a perpendicular being dropped from the right angle, then all three triangles that are made are similar. Okay, and there's a reason for that. It's perpendicular from a right angle triangle. So the first thing we've got to write down is, why is angle P1 plus P2, or angle LPN, why is that 90 degrees? Right, well, LPN is 90 degrees because it's an angle in a semicircle. Angle in semicircle. Okay, so therefore, now we're given that LRP is 90 degrees. Okay, given. And so therefore triangle LPR is similar to triangle LNP. And our reason here, just perpendicular from 90 degree angle. Okay, so that's that. The next part of the question, and we're starting to see a pattern here. When we prove similarity, the next part normally involves using the similarity. The next part says if LP is root 6 and RM is 2. So this little piece here, LP is root 6 and RM is 2. And it asks us to find the radius of the circle. Now, obviously, if we could find the diameter of the circle, then we would be there. Let's see if we can pull some sort of ratio out of here. Okay, now we know about LP. So let's start with LP. If we put LP, what must we take from the other triangle? Well, we must take LN. Now, LN, we don't know, but it's not too bad. It's actually what we want to know. LN is actually the diameter. Okay, right, let's see what else we've got. We don't know PR. Okay, what about LR? We do know something about LR. Okay, so if we took LR, then we'd have to take LP again. LR over LP. Okay, now the reason we can pull out this ratio is similar triangles. Okay, if we cross multiply here now, we're going to get that LP squared is LR times LN. Okay, now LP squared is obviously just going to be 6. LR, okay, LR is a radius. From M to L is a radius, and we've got 2 here. So this is actually a radius minus 2. And LN is actually 2 lots of a radius. Okay, and so that's maybe also a little bit tricky, because the idea of letting the radius be R. Okay, so now what we've got is we've just got an equation which we should be able to solve. Let's take out the brackets, 2r squared minus 4r, and let's subtract the 6 from both sides. Let's now divide both sides by 2, and we get r squared minus 2r minus 3. And let's see if we can factorize that. And it factorizes, in fact, to r minus 3, r plus 1. So r must be 3. The radius is 3. R can't be negative 1. So the radius of this circle is 3. Okay. Again, quite a tricky question. Okay. Let's pause the video. I think this one's a little bit simpler. Pause the video, try this question, and then we'll let it play again and see how you went. Okay, so when we look at this diagram, we told about the parallel lines, which we can see. We can also see that we've got a diameter. We know things about diameters and semicircles. We can also see that we've got a tangent. Okay, so the first question says prove that CT is equal to TE. Okay, now if we look at CT and TE, they are on a chord, all right? And we know that if this angle here is 90 degrees, if this angle in here at T2 is 90 degrees, then that chord would be bisected. Okay, so now let's change the question and ask ourselves, well, how can we prove that that angle is 90 degrees? Okay, well, if these lines are parallel, okay, then if this one's 90, this one would also need to be 90. All right, so let's start off by saying, can we prove that E3 is 90 degrees? Ah, yes, E3 is in a semicircle. So let's write that down. Angle E3 is 90 degrees. Angle in semicircle. Okay, therefore, angle T2 is 90 degrees. And the reason for that is because you've got these two co-interior angles. Co-interior angles. But remember, when we use co-interior angles, we must say which lines are parallel. Line OT is parallel to EL. Okay, now because that's a 90 degree angle, okay, because this yellow one is a 90 degree angle, CT will equal TE. CT equals TE. And the reason is perpendicular from center. Okay. Right, then in B, prove that COEK is a cyclic quadrilateral. Just a reminder that even if we couldn't do part A, we now know that CT equals TE. Okay, we're now trying to prove that this thing is a cyclic quadrilateral. Okay, and remember we've got four ways of proving a quadrilateral cyclic. Opposite angles supplementary. Opposite angles add to 180. That's one. Exterior angle equals opposite interior angle. That's the second way. And the third way is to try and use the converse of the angles in the same segment. Okay, and that looks kind of something like that. Okay, so perhaps you want to pause the video again and now look at these 4 points. So we're talking about, I'm just going to go over COEK. This is not actually, they're not kind of all sort of joined up, so we're looking at these 4 points. We're asking, do those 4 points form the corners of a cyclic quad? Okay, and I guess it comes with practice, but I'm actually wondering if we could show this angle here equal to this angle here, then we'd be done. Okay, if we could show angle C equals angle K. All right, now what do we know about angle C? Let's start with angle C. Okay, angle C is actually the same as L4. All right, let's write that down. Angle C is the same as angle L4. Anyone see why? Tan, chord. All right, but what do we know about L4 and K? L4 and K, and it might help to sort of turn the diagram slightly, but we've got these parallel lines here, there, and there. L4 and K are actually corresponding angles. So, but L4 is equal to K. Corresponding angles, don't forget to mention the lines which are parallel. OK parallel to EL. Okay, so therefore we actually have proved that angle C equals angle K. We don't need a reason for that. That follows from above. All right, now if angle C equals angle K, we've got our sort of even van butterfly bow tie. So therefore, COEK is a cyclic quadrilateral. And the reason is the converse of angles in the same seg. Okay, not too bad, not easy, but not too bad. All right, next up, we need to prove that triangle COT is similar to KET. I'm going to do that up here just so I can see the whole diagram. So I'm going to try and prove that triangle COT is similar to KET. Now, even if we couldn't prove the cyclic quad, we can assume that these 4 points are the corners of a cyclic quad. So we're talking about COT and KET. I'm just going to clear some stuff off here. All right. I'm going to clear everything off. Okay. We're talking about this little triangle over here and this bigger triangle over here. We're trying to prove them similar. Again, there's two ways of proving triangles similar. One is to use corresponding sides, and the other is to use angles. You would have seen that angles are much more common. We're not given any sides here. All right, let's try and answer C over here. So what we know straight away is that T1 is equal to T3. And the reason for that is vertically opposite angles. Okay, but we also know that angle C equals angle K. And even if we couldn't prove the cyclic quad, those are angles in the same segment. So the third angle in each triangle, O1, will actually be equal to angle E1 and E2 or angle TEK. We've got choices here. Those are actually equal because of angles in the same segment, but they're also equal because it's the third angle of triangle. And so now these two triangles are similar. COT, if I start with C, I must start with the angle that's equal to C, which is at K. If I go to O, I must go to the one that's equal to the one at O, which is this one here, E. And then the angles at T are those two, and those are the ones that are equal. So triangle COT, similar to triangle, sorry, let's just try and write that a little bit better. Triangle COT, similar to triangle KET. And the reason, angle, angle, angle. Okay, let's see if there's anything else in that question. It says if OT is 1 and KT is 9, find CT and CO. Right, I think we're going to need to use the similarity here. Okay, we've told OT is 1 and KT is 9. KT is 9, all of that. Okay, so and the question's asking us to find CT. So let's see if we can pull out a ratio over here. Well, if we take CT out of the first triangle, we must take KT out of the other triangle. Then we're going to take OT, perhaps. If we take OT, we must take ET. Okay, and the reason that we can do this is because we've got similar triangles. Now let's see what we've got and what we don't have. CT, we don't actually know. That's what we're trying to find. But notice that CT and ET are the same length. Remember, we proved that right at the front. So that is equal to that. So instead of having CT and ET, I can have CT times ET is going to be OT times KT. Now, OT times KT, I know those. So it's 1 and 9. Instead of writing CT, ET, I'm going to write CT squared. Okay, and that's because ET and CT are the same. So now, CT squared is 9, so CT must be 3. Okay, and then the last question that we get asked for is, what is CO? Right, now CO is going to be the radius of the circle. Okay, and if I know this, remember this is a 90-degree angle here. So this is 90 here. I can now use Pythagoras. Okay, CO is going to be 3 squared plus 1 squared square rooted. CO is going to be the square root of 3 squared plus 1 squared. And the reason for that is Pythagoras. Okay, so in fact CO is the square root of 10. Okay, I apologize for the sort of writing all over the place, but I do need to be able to see the diagram while I'm doing the question. Okay, right, we're going to, that's the end of that question. We're going to stop there. Before the next lesson, start on page 48 and try the question on page 48 and 49. We'll look at it with you next time. Right.